Hello everybody, I'm going to start now the course, Introduction to Distributed System. So my name is Seif Haridi, I am the course leader and I'm going to have some assistants to help you during this course, Qasem Arad and Talat Shafat. They are going to participate in the discussion forum. So we start with a simple question: what is a distributed system? And here is a definition of distributed system that is actually given by a known researcher in this area, Leslie Lambert. So Leslie says that a distributed system is a system in which the failure of a computer you didn't even know existed can render your application or your computer unusable. So what did he mean by this? He really means that a distributed system is actually a system consisting of many machines working together. Your machine is just one part of this. And if your machine is depending on other machines and their functionality, their application, if any of these fails, your machine will not work. Think of a situation where there's another machine in the system which is a, say, file system. Your machine is running an application that depends on that file system. If that file system fails, your machine cannot perform its application. So really, what is a distributed system? So a distributed system in this course is actually a set of nodes. Nodes, that is computers, machines, connected by a network. And they work together to do some service or some application. That's why we say that they appear as a single coherent system. So what are we going to do in this course? We are going to focus on concept underlying distributed system, different kinds of computation models for distributed systems, and actually many basic algorithms and abstraction that are used to build fault-tolerant systems. So why do we study distributed system? First of all, every system today is really a distributed system. Think of the internet. The internet is a distributed system, set of nodes. The nodes are in the routers, in the core, and the user machines or the servers at the edge. Think of the World Wide Web and of, say, a system of a set of small devices, mobile, smartphones connected together. You can also study distributed systems because of technical issues. For example, you want to have a service and you want to improve the scalability of this service. You improve the scalability of this system by, instead of having a single machine, you can have multiple machines connected together performing the service. And if this, for example, a web server, then this can serve multiple users instead of a single user. Requests can be sent to the different machines to perform the service. You can also use distributed system for reliability, where think of you want to replicate a service. So the service exists in multiple machines. If one machine dies, the other machines can take over. And if you think about it, so distributed system now is quite popular. Think of cloud computing, which consists of multiple machines residing in a data center, and these together perform multiple services to many users. You can also think of distributed system because the system itself is distributed. So the system is located in different places geographically, and that is the best thing for the system to work. Here is an example where building a small distributed system was important to reliability. So PAS was a computer developed by IBM in '81 and is used in the space shuttle. This computer could have been done or built by a single node, but if that node dies or crashes, then the shuttle will not work. So what was this computer? It's a control computer of the shuttle. It takes input from sensors of the shuttle and make a decision, and then initiates or some actuators, depending on the decision it took from the sensor input. Okay. So what they did is that they have 4 machines instead. These 4 machines, they work together and they perform voting. In each output they want to perform. So that, and once you get a majority, you perform that output. So if one machine dies, still the others could perform the service. It was also used to develop this control program, by different teams, so that if there is a software fault in one, still the majority, if they agree, they can continue perform. So why do we study distributed system? We study distributed system first of all because it's interesting and challenging. There are 2 issues that are important when you try to make a distributed system work, and depends, of course, in the underlying system. Distributed system exhibits something that we don't see in sequential centralized programs, which is partial failures. By this I mean you have a set of nodes connected by a network, but the network can drop message or can partition. So that is one possible failure in the system. The other is that some of the nodes can crash, can fail, but still the system as a whole should be able to work. The other issue is concurrency. So if you want to build a distributed application, it is in fact a concurrent application. There are parts of this application running in each node in the system. So it executes in parallel and message travel asynchronously. Normally, when we talk about concurrency, we think of parallel computing. We use program running on multiple machines to improve performance. And that is part of distributed systems. But still, the other important part is still some of these nodes might fail. So distributed system handles both concurrently and partial failure. So what we are going to study is what we call a recurring core problems in distributed systems, and these problems are actually, I can say, also basic services that you want to build because it could be reused in many distributed applications. Okay, so what type of problems there are? Before we start this, we look to just a simple problem. It's just to tell you that actually distributed systems are not that easy to build, and the common intuition of things working on a centralized machine will not work in a distributed setting. So let us look to the two general problem. And here is the problem, and see if this problem can be solved or not. So we have two general need to coordinate an attack, and two. So the generals are here. They need to coordinate an attack. They are situated in different places. And to coordinate this attack, so what they do, they want to agree on the time of the attack. And they will win only if they attack simultaneously. And they do this by sending a messenger. So a messenger goes from one to another telling, so General A is telling General B, let's attack tomorrow at 8 o'clock. And if they agree, then they will attack, as I said, and they can win the battle. But what can happen is this messenger could be killed in their way. Okay. The question, can we build a service or a program that really perform this task? So let us see. So let's try to solve the problem for General G1 and General G2. Okay. So General G1 sends time of attack to General G2. This is the first thing he does. So we know that this messenger can be killed on the way to General G2. The problem now is how to ensure that G2 received the message. So one way to think about it is to assume that General G2 will send another messenger with an ACK, an acknowledgement of that he has received the message. Fine. But now we have another problem. How do we ensure that G1 received the ACK? To solve this problem, we let General G1 ACK the receipt of the message. And that can continue on and on without finding really a solution. Remember here, we are talking about a distributed system, so the only way for these two generals to communicate was through a messenger that travels between the two generals. Actually, this problem is impossible to solve. It can be shown that it is impossible to solve. So you see that in distributed system there are things that we want to do because of problems that are impossible to solve, and we have to cope with this when we are building these systems. Okay. So the applicability of the two general problem. So what is the two general problem? It is two nodes need to agree on a value, and they communicate by messages using unreliable channel, and they want to agree. And it happens to be in a system where we don't know how long time the message can traverse from the sender to the receiver, or if the message can be lost. It happens to be that we cannot solve this problem. As you can see, what we have been discussing here is actually a problem that is the core of many fault-tolerant distributed systems, which is agreeing. Agreeing in this case on a number, agreeing on a value. So this problem is called consensus. And consensus problem is a problem where all needs propose a value, and some nodes might crash and stop responding. And the algorithm has to ensure that all machines that do not crash, which we call correct nodes, eventually decide on a value, and every node will agree on the same value, and the value decided is only one of the proposed. So you can think of it this way. Here is consensus. We have nodes propose, and here we get a decision, and this decision should be a single value, and every node should be informed by this value. So consensus is an important problem. So in databases, concurrent, where you have multiple transactions, you have concurrent changes to the same data, nodes should agree on the changes. For this, a special kind of consensus is used called atomic commit, where the nodes involved in a concurrent transaction only propose two possible values, commit and abort. Another problem is broadcast, where in particular we are talking about atomic broadcast. In this case we have sets of nodes, a set of nodes. Any node can broadcast a message, and this message should be delivered to all the nodes in the system. So we have a node broadcast a message, and if the sender does not crash, all correct nodes deliver the message, and all correct nodes deliver the same messages. But more importantly might be that all correct nodes deliver the messages in the same order. So why this is important? This is important because we can use the broadcast abstraction or the broadcast service to implement a replicated service. A replicated service, the service consisting of set of machines. When they receive an operation, they all perform the operation. And if they receive the operation, multiple operations in the same order, then they will perform these operations on the same order using an atomic broadcast. Therefore, the state given of these machines, given that the machine, each operation is deterministic, will be the same after performing these operations. So it happens to be that the problem of atomic broadcast and the problem with consensus are equivalent problems. And by this I mean, given an atomic broadcast service, we can implement a consensus service. And the vice versa. Given a consensus service, we can implement an atomic broadcast service. So let us see how we implement consensus using atomic broadcast. So here is a solution. Every node broadcasts its proposal, and every node decides on the first received proposal, and all messages are sent in the same order, so they will actually decide on the same value because it is the first message we decide on. Now I will let you think how, given consensus, how we can solve the problem of atomic broadcasts. It's up to you to solve it. And it turns out that atomic broadcast is equivalent to consensus.